This work was done with a student at Indiana University, Arch Sila-Pirudi, and it looks at the relationship between sensitivity, similar non-matches, and database size in fingerprint database searches. And to help us understand why this is a particular problem, consider the following two scenarios. In the first, a detective or a latent print examiner develop a print from a crime scene, and the detective has a suspect from cell phone records. So you as an examiner compare the prints, and you decide if it's an ID or not. The second scenario is that you develop a print from a crime scene, but then you search that print against an AFIS system, and then you develop a suspect using the AFIS database, and you compare the prints. In scenario one, the likelihood of an incidental close non-mated pair that could lead to an erroneous ID is very unlikely because these are two sort of sampled at random. In scenario two, could the likelihood of a close non-match depend on the size of the database? After all, it's the job of AFIS searches to return similar-looking prints. Well, Dror and Mnookin suggested the answer was yes. And we decided to simulate this to find out whether it's possible to have a database be too big. And this work was recently published in the journal Law, Probability, and Risk, and it's actually currently in press right now, so we don't have an exact timetable for publication. So imagine that you do AFIS searches with known prints and you record the AFIS scores for the matching print and the top 19 non-matching prints. So basically you record the scores for the first 20 on the first page. And then we'll repeat this simulation 10,000 times, each time with a new print, and you know that the mated pair is in the database, and you record all the scores that you observe. So let's create a frequency histogram of all the scores that we observe here. We're going to use what's called a discrepancy score, which is basically a measure by the algorithm of how similar a print or an impression in the database is to the print that you submit. So a perfect match would be 0 in our score, because that would be all of the features being exactly identical in location and shape and appearance. So if you simply submitted the same print that was already enrolled in the database, presumably you'd get a discrepancy score of 0 here. Now, due to distortion or partial prints, the discrepancy score is unlikely to be 0. It's unlikely to be some larger number indicating some dissimilarity between the submitted print and the prints that are enrolled in the database. And that's what is illustrated here. The x-axis here, so the discrepancy score is how similar each recovered impression is relative to the search print, where 0 is a perfect match. The x-axis on this graph is a discrepancy score that you record for each print that's returned from the database. So this is just the score returned on the AFIS screens. The y-axis is the number of times you observe that score for the mated and non-mated prints. So the mated are in blue and the non-mated are in green. And here you can see that the blue points, those come from the mated distribution, or the mated prints, and they're going to have, in this, according to this matcher, they're going to have scores that are lower than the non-mated impressions. And this sort of makes sense because, of course, the mated pairs make the same impression, or at least a similar impression. So what this is telling us is the degree of overlap between the two. Now, we're just simulating these here, and you can imagine that the amount of overlap that we've shown here is actually a bit misleading. So let's actually consider a scenario where the overlap is not as great. So here is the overlap you would observe if the AFIS matcher was better. It would understand that mated pairs are very similar to each other. The impressions are very similar if they're generated by the same finger. And if two impressions are generated by different fingers, the matcher is good enough to determine that those should have higher discrepancy scores, meaning there's less similarity. So the amount of overlap depends in part on the performance of the matching algorithm in the AFIS system. Here we have a better comparison algorithm, and that provides better separation between the mated and non-mated prints. And then you can imagine even a better system that has even less separation between the two. Here's a third algorithm that provides even better separation between the mated blue and the non-mated green prints. Now, because we don't know how good an AFIS system is, and they're always improving, we will simulate different amounts of separation between these two to illustrate how the performance of the AFIS system might affect this problem of increasing database size and whether that creates problems. So, do large database searches create problems? Well, as we showed in the last three graphs, the amount of overlap can vary. However, note that it isn't the average AFIS score of the non-mated prints that gives problem prints. It's the minimum AFIS score, or, well, maximum if you have an AFIS system that uses larger numbers for more similarity. But the close non-matches, those prints that would create a potential problem, a potential erroneous identification, where you say, that's the guy, that's him, and in fact it's not him, so you're putting potentially an innocent person in jail, those are created by situations where you have a very close non-match returned by an AFIS system, close enough to fool an examiner who's not being careful. So the minimum values are those close non-mates that are suggested by the AFIS system that could lead to erroneous identifications. As we will see, these problematic close non-mated prints are the function of both how good the AFIS matcher is, but also how many prints there are in the database. So let's just start with a simple example of searching a database with just 100 impressions, just to see kind of what this looks like. So these three graphs here are the different types of AFIS searchers. So the three columns represent the performance of the three types of AFIS matchers that I showed previously, the poor, okay, and really good. And the x-axis is the discrepancy score. That's basically for the prints that are returned, what is the score that the AFIS system gave them? The y-axis is the frequency we observe the discrepancy score of this value. Now, the blue curve is essentially identical to the blue curve that I showed in the previous graphs. The green curve, however, is different. It's actually the minimum of the non-mated pairs, because it's the minimum that is the one that's going to screw you up. That's the one that's going to give you a close non-mated pair, non-mated print that could potentially lead to an erroneous identification and therefore a erroneous imprisonment. And this is clearly what happened in the Mayfield Madrid print, where Mayfield's print was recovered by an AFIS system and deemed similar enough to warrant the arrest of Brandon Mayfield. Well, here you have a good AFIS algorithm that has very little overlap. There's less good AFIS algorithm here, and there's lots of overlap. So we don't really know which one of these scenarios we're in, but the more overlap you have, the more the non-mated pairs may start looking like matches, leading to possible erroneous identifications. All right, well, this is just for a dataset size of 100. Let's increase the database size from 100 to 1,000. So this might be like a citywide database or small city or something like that. Well, something interesting happens here. First of all, the blue distribution stays the same because it doesn't shift. It's not a function of the database size. There's only one matching print in the database for that suspect, and the value that's returned is just the value that's returned. Now, of course, each time you make an impression, it's going to vary slightly, which is why they're not all at 0. But the blue distribution is not a function of the database size. The green distribution, however, is a function of database sizes, because you can see that even going just a factor of 10 bigger, we're starting to see more overlap between these different distributions. In fact, it looks really bad on the left-hand side here, because as these curves start to overlap, that suggests more close non-mated prints are recovered from the database. And this results in potential problems that could be increasing. We start to worry when the green distribution starts dominating the blue distribution, being more to the left of it. We seem to be okay here, where the blue distribution is clearly to the right of the green distribution. Well, this is a pretty modest size of AFIS systems here. The FBI database has 900 million prints, so let's go big. Let's go for 1 million and 10 million prints. Well, now we can see that there's a lot of overlap between the two different distributions, and in fact, for our weak AFIS searcher here, the minimum of the non-mated pairs is much, much smaller than the mated pairs, suggesting that the first 3 or 4 screens of an AFIS search may be dominated by non-mated pairs, and an examiner may not get to the mated pair if it's in the database. Even worse, they might discover that the mated pair, that a close non-match, a close non-mated pair, looks similar enough to conclude that there is a match. And they call it an identification, and that could lead to another Madrid problem. So notice even with our relatively strong AFIS matcher here, it has some overlap, and the poor algorithm is more likely to recover a non-mated print than a mated print in its top position. So these large databases have a lot of overlap between the closest non-match and the mated pairs. Here are all of the graphs, and this is a little bit small and I won't dwell on this too much other than to show that for all of these different AFIS matchers, the relatively poor one here to the relatively strong one here, as you increase the database size, which is what we're doing as we go down each row, we can see that the non-mated pair distribution starts creeping to the right while the mated pair distribution stays the same. And we can see that in some cases the non-mated pair completely dominates the mated pairs, suggesting that there are many, many close non-mates on these first pages that are pushing the mated pair lower and lower into the AFIS search screen, into later and later search screens. So that's not good. But is there a flip side? Do large databases create opportunities as well as problems? Well, of course, larger databases are more likely to contain the suspect. That's the whole point of using larger databases. The probability of finding the suspect in the database will grow, and in our case, we assume linearly with the size of the database. This is probably not completely accurate given a geographic model of crime, where as you increase your database from a city jurisdiction to a county to a state to a national jurisdiction, you're less and less likely to find the suspect in the database because crime tends to be more local. But it turns out that breaking the assumption of it growing linearly only makes the problem worse that I'll describe. So the problem of more close non-mated pairs being returned by AFIS grows non-linearly. So we've got the good thing growing linearly, we've got the bad thing growing non-linearly. And these two factors will trade off against one another. So we need to figure out how these trade off and whether there's an optimal database size, and is it possible to have a database that's too big? So we're going to ask, is there an optimal database size? Well, let's summarize the overall sensitivity of database search by considering two things. The first is the likelihood of the suspect being in the database, which is basically the degree to which close non-mated prints could lead to an erroneous identification if the suspect is not in the database or if it gets pushed off the first set of pages. So the first one here, the likelihood of the suspect being in the database, that grows linearly with the size of the database. The second is, and I'll need to put this in, the second is that the degree to which the close non-mates could lead to an erroneous identification, that grows non-linearly. So we're going to compute the ROC curve and derive the area underneath this curve. Let me show you what I'm talking about here. So here are the graphs that we showed a moment ago. To compute the ROC curve, we're going to set an arbitrary criterion for declaring an ident. We'll sweep this across and calculate the cumulative density under each curve. So we'll start here, and this will tell you the probability of observing a mated pair or close non-mated pair at each value. So we're going to sweep this criterion and calculate the area under the curve to the left of each distribution. So we'll set an arbitrary criterion here and calculate the area underneath the green and blue curves. Then we'll do it again, and we'll do it again, and again, and again, and again, and sweep these all the way across. Now here is probably a good example in the upper right. We can see that almost all of the area of the blue is to the right of this distribution, and virtually none of the green distribution is to the right of the, to the left of the criterion. So almost all of the blue is to the left, and almost none of the green, just this tiny little slice right here. What that means is that we'll have high sensitivity because there's a lot of overlap, there's relatively little overlap between these two different distributions. Here, on the other hand, if we go back to this scenario right here, this is a terrible situation because almost all of the green is to the right, to the left of our criterion, and almost none of the blue. This will actually give you a very, very small sensitivity value because it's actually upside down in some sense. You want the blue curve to be to the left of the green curve, and this is the opposite. So this is a way of characterizing how good the database is overall. And we'll calculate the area underneath the curve. We also need the probability of the suspect being in the database, because not all suspects will be even in the larger database. Everyone has a first crime, and crime tends to be geographically clustered. So we need to discount the mated pair distribution because somehow sometimes the mated pair will not be in the database to be found. So to do this, we're going to simply calculate the probability of the suspect being in the database as a linear function of the size of the database. And we'll just asymptote this at 80%. You can use other functions too that are a soft asymptote. Doesn't really matter. It just has to grow monotonically with the size of the database, close to linear growth. We're going to multiply this probability by the cumulative density for the mated pairs, essentially discounting the size of the area underneath the blue curve. So here's a quick summary of the good and the bad. Larger databases have more prints, which increases the likelihood that the mated pair will be in the database. This grows linearly with the size of the database, but gets capped at 80%. And this is the good side of larger databases. The larger the database, the more likely the suspect will be in the database. But larger databases will also return more close non-mated prints, which could lead to erroneous identifications if the examiner isn't careful. And this grows at a rate that is nonlinear. This is the bad side of larger databases. So how do these good and the bad trade off as the size of the database increases? Well, to determine how these trade off, we compute the sensitivity of the database by computing the area under the ROC curve, which reflects the degree to which the mated pair is both in the database and is not dominated by close non-mated prints. Because the close non-mated prints will potentially push the mated pair off the first several screens or cause the examiner to select a close non-mated print as an ID before seeing the true mated print. And that could, of course, lead to an innocent person going to jail. So sensitivity is an overall measure of the utility of a database without considering the cost of different kinds of errors. All right, so here's the sensitivity graphs for our three kinds of matchers, shown in blue, green, and red. So blue is the really poor comparer, green is the relatively good, and red is the excellent comparer. The x-axis here is the database size, ranging from 100 prints here to 1 billion prints here. The y-axis is sensitivity, and the higher you are, the better. This goes from 0, essentially no sensitivity, all the way up to 0.8, which is in theory, the area could go up to 1, but in our scale it goes up to 0.8. Greater sensitivity means less probability of finding a close non-mated pair that might lead to an erroneous identification, as well as a greater likelihood of finding a mate. It's a way of characterizing the trade-offs between these two things. And what we see is that as the database size grows, moving from left to right here, sensitivity for all three of our comparers increases. But for all three, at some point it reaches a maximum, and then it begins to decline. And we see that even for our very strongest matcher here, it reaches a maximum here and then starts declining. What this illustrates is the costs of searching a larger database outweigh the benefits of possibly finding the suspect. Because if you search against a national or international data set here, you're getting an incredible influx of close non-mated prints, which could cause an erroneous identification, like we saw in Mayfield. But the chances of finding the suspect are going down, in part because the larger databases are exposing you to geographic areas that the suspect is unlikely to be enrolled in. So there is an optimal database size. Increasing the size of the database will make it more likely you'll find a suspect, but also expose you to more potential close non-mated pairs. Eventually, the close non-mates overwhelm the true mates, and our recommendation is to search the largest database that you reasonably think would contain the suspects, because larger database search results should be viewed only with extreme caution, as they might contain close non-mates. Now, an actual AFIS system interaction would be required to specify the exact optimal size, so we don't really know exactly how big is too big. And we also would need a geographic model of criminality, which could be crime type dependent. But all of this illustrates the dangers of just arbitrarily searching the largest database that you can, because you're going to be overwhelmed with lots and lots of close non-mated pairs, which could potentially lead to erroneous identifications, or bury your actual true mated print, the actual suspect, so deep into the search pages that you'll never go through and find them with a manual search. So stick to that database that you think would reasonably contain the suspect. Maybe if it's like a terrorist crime, you think the terrorist moves around, that makes sense to go to a large database. But if you have a robbery suspect and you think that that person is operating in a very small area, search the city and the county database and maybe the state database, but don't go to the FBI automatically. That's a very dangerous proposition.